Any questions till what we have done today? Right. How much energy do you have for me to start a new topic now? So tomorrow is the last day you will see me, because the last few days of the course will be taken by the local course coordinator, Professor Murlidhar and Professor Sri Harirao. Okay. I will cover, the plan for the day was I would have covered all of this in the morning, but then I was asked to give that career lecture, which didn't make much sense. And then we would have covered thermal sensors, sensors to measure heat. So what I will do is I will do a brief introduction to thermal sensors now. The exact sensor we will cover tomorrow. Okay. This is more as a pitch, and tomorrow we will leave more time for one-to-one discussions as well. So we'll leave the second half as much as possible for doing problems as well as any one-to-one discussion which you would like to have it. Now, temperature sensors are very interesting species, in the sense that you could have sensors to measure the temperature of your own chip. We don't want the chip to get very heated. Or we could be looking at infrared sensors. Now, infrared spectrum, visible spectrum is small. It's 380 nanometer to 700 nanometer, red. Anything beyond red all the way till very, very high frequencies is infrared. The spectrum is very, very broad, and it does a lot of things. There are some freely available books. You have these references to Budzia and Gerlach. I found it very easy to read myself. Now, anything between visible, which is 380 to 780 nanometer, and microwave, which is 1 millimeter to a meter. So anything from 780 nanometer to 1 millimeter is infrared. All of this carries heat. Now we have an infrared sensor in our eyes. Have you guys ever tried going out on a sunny day and closing your eyes, and you can still see a silhouette of other things, right? You have closed your eyes, you have put the mechanical shutter on. So why are you still seeing something? You are seeing the infrared, which is not stopped by these. It passes by and our sensors still pick them up. Okay. So what we generally divide is in few regions: near infrared, mid infrared, and far infrared. And just a quick summary of what these are. Ignore the numbers. Okay. The best way to visualize that is near infrared is the one close to red. Okay. And at this point, the infrared is being produced by hot bodies, which are more than 1000 degrees Celsius. Actually, the sun produces about 6000 Kelvin, and the electromagnetic spectrum it produces is maximized at around 600 nanometer. And there's a theory that that's why maybe we are highly sensitive to green, because we evolved with the sun. We wanted to see the sun. We wanted to see the central frequency which is coming from the sun. Why we are only seeing that visible spectrum? Why are we not seeing infrared, ultraviolet? It's either a scientific question which we'll answer after many years, or I will ask when I die and go up to the Lord. If there is a God, I have to ask the question. Why are we designed in these particular spectrums? Then the less hot the body is, higher the infrared spectrum it produces. So if you take something which is, say, our human body, we also infrared spectrum produces, but that is far infrared. We are producing in tens of 10 micrometer dimension of infrared. Okay. And then you also have ultra far infrared, which are looking at things like these. Mid infrared are hot objects, things like close to your cooking voltages, if you take a mid infrared there. Now, one of the reasons why I said this, now you can immediately see each region has a different application. So you might be looking at contactless temperature measurement. You want to measure my temperature without coming. So you're looking at one particular infrared region. I'm not a very hot object. Well, if I am already at 1000 degrees Celsius, I think you have other things to worry about than my body temperature. Agreed? There are heat-seeking missiles which are trying to identify a certain heat pattern. There are the beauty of infrared is generally not affected by things like darkness. Even when visible light is not present, we are still producing the IR, fog, and hence it can be used for measuring things like movement. Even when there is a dark scene outside, we can use infrared sensors to measure movement. The other advantage, other difference we have here. So what should we see infrared as? Should we think of it as heat, or should we think of it as an electromagnetic wave? Because both could mean two different sensors. Remember, I said everything is a thermal sensor in electronics. Diode current changes, resistance value changes as you heat it. So everything can be used as a thermal sensor. But that's the heat-based sensor. We made diode as wavelength-based sensor, right? It measures a certain wavelength, 600 nanometer. We can think of sensors like that as well. Considering both of these are in here, that's a signal for me to stop for today. So I will stop for today, and tomorrow we will go and look in both these modalities to measure temperature. Temperature as measured here, wavelength as heat as measured as a wavelength. Now we are looking at specific things, or as measured as heat. Heat is never one wavelength, right? We have got broad wavelength of heat produced. So both of these thermal sensors we will see. So the plan for tomorrow would be, we will see thermal sensors to measure the rest of the world. Then we will see thermal sensors to measure inside the chip. Chip is also getting hot, and we need special kind of electronic thermal sensors. The last sensor we will look will be a bit of, let's see if we can do gas sensors tomorrow. If not, we'll certainly do pH sensor, which is a chemical sensor. So many chemical reactions happen when the pH of something is changing, or pH of changing something denotes a chemical is reacting. And we'll be looking purely from electronics point of view how we can convert a transistor into a pH sensor. I think that should be enough for a course. Otherwise, if I keep on teaching, after a while you guys will just forget the entire word of spectrum. Good. Then thank you very much. Enjoy your Thursday. Thank you. Be dead by then, because my head is thumping right now as if it wants to do something else. Okay. We started here yesterday, and we started talking about, we are trying to, the first part of the lecture will not necessarily be on temperature sensor, but let's start off thinking of them as infrared sensors. So we have done visible light from ultraviolet to partly red, and anything beyond visible is, and below microwave, counts as part of infrared. Because it's a very broad spectrum, I mean, look at this way, 380 to 780 is roughly visible. That's 400 nanometers, right? And then you go for 780 nanometer to 1 millimeter. How big that range is? It's almost a millimeter range, because after nano you get micrometer. So 1000 nanometer will be roughly 1 micrometer, and then you go 1000 times more, you get a millimeter. So it's a very broad range of intensities which we are looking at in infrared measurement. So we often divide it into a couple of few, 3 or more. There are many sub units of there. So we started talking and said visible light covers the various colors which you can see. Near infrared is a response coming out of very hot objects. We are looking at 780 nanometer to 3 micrometer here. A thing to see is also the photon energy. Some of you who were not there in the first day, we calculated the photon energy of visible light photons. How do you calculate photon energy? What's the formula? hc by lambda or h nu, where nu is the frequency. So, it is Planck's constant multiplied by the frequency of the radiation, or Planck's constant time the speed of light divided by the wavelength of radiation. The reason why it is important will become apparent very quickly. We did this earlier, but I will do a revision just to remind us where we are. As you go further higher in frequencies, this is where we are looking at room temperature or normal heat, 300 degrees Celsius, or even higher in bodies at room temperature. So, something like I and you will be having a photon energy of the ballpark of around 0.05, 0.1 electron volt, and mostly radiations in the terms of tens of micrometer of wavelength. Of course, there are things even before that. So, you will see these words more frequently: near infrared, mid infrared and far infrared. And then also see ultra far infrared, how far it is from visible ranges. Do not forget, the further we go, the photon wavelength increases, but its energy starts going down. Okay. Application wise, we have got a large number of application of infrared sensors. We can do contactless temperature measurement, and once you can do temperature measurement, there are many things you can know about a material. Generally, such measurements are not affected by visible drawbacks, things like darkness, fog, and sometimes even small objects falling in between there. So, for example, our clothes, IR radiation can generally pass through that. The other big application of IR is an IR spectroscopy. When we are trying to figure out what material we have, a number of materials or atoms of this material absorb certain wavelength in infrared. So, if you look at which wavelength is being absorbed, you can then say what material we have. A carbon dioxide is a very good example of how it can be measured by looking at its absorption spectrum. And then of course, but if we have temperature profile of something, we can, and that something is moving, we can identify just looking at the temperature measurement rather than having to look at this visual picture. Okay. Particularly if you have night vision cameras and you are trying to figure out if there is a human person moving or not, they are mostly looking at infrared domain. But as you can see, it depends upon what you are trying to measure. If you are trying to measure human beings, we should be making a sensor in far infrared domain. Okay. Then of course, the question is, what do you measure? Now, there are two things here. One is, okay sir, one is you measure heat, the other is you measure a wavelength. Heat is generally broad spectrum, and the way you measure heat is, your transducers will convert heat either directly to a voltage or to something intermediate. That something intermediate could be temperature, could be pressure, could be strain, could be stress. And a very good example, if it converts to temperature, then we can measure that temperature through indirect means, okay, through other sensors. Now, generally heat measurement is wavelength independent. You are not measuring a particular wavelength, you are measuring how much energy it has, overall energy it has. Now, here is a problem of heat measurement. It also heats my sensor. Right? Ideal sensor should measure heat but should not be affected by it. That is not going to happen. Right? So, quite often in many of the other sensors like wavelength dependent sensors, we try to reduce the temperature or cool the sensor to record the infrared. To some extent it also helps in, because you know at room temperature, at any temperature, we already have thermally generated charge carriers as well. In any semiconductor, heat itself leads to electron hole pair formation. Ideally, we would want to measure electron holes which are just being produced by my radiation, not by my heat. So, heat produced, ambient heat produced electron hole pairs, they are like noise to me. or my leakage current. Even in photodiodes, in pixels, heat produces electron hole pairs. So, one solution to that is to cool the sensor. Now, this is particularly when you are trying to record very low amount of intensities. A very good example is when we are looking at light coming from stars. Now, some of the stars we can see by our naked eye. A number of others we use telescopes of different type. The amount of light coming from these stars is very, very low. So, quite often we are looking at few photons, a few hundredths of photons. If our sensor itself is producing 100 electrons as part of thermal noise, I will not be able to read these 100 photons. So, 100 photons will produce 100 electrons. My sensor noise is, say, not even 100, it is 50. Then my noise to signal to noise ratio is quite low. So, quite often in these extreme applications, we cool the camera and cool it to very low temperatures, sometime at 4K, sometime at around 70 or 80K. And at that temperature, we believe that, well, the thermally generated charge carriers will be low, which means whatever we will be measuring will be intensity effects. However, for heat based sensor, that does not do much good. Cooling does not help. Cooling helps with sensors which are measuring infrared radiation. The other drawback of heat based sensors, they are not very good in frequency domain. They can only measure up to 100 hertz. You need the heat to affect my sensor. You need it to have a temperature change. And as you know, temperature change generally takes time. Right? Most material have got an inherent ability trying not to heat. And typically the relationship is of the order of T to the power alpha, alpha depending varying from sensor to sensor. The other alternative is we measure, think of heat as photons. It is an electromagnetic radiation. We talked about heat covers everything from visible all the way till a millimeter of radiation. And then the design becomes very much like you design a camera. So, towards the end of it, we will do a camera design with heat measurement things. Okay. Of course, you have to choose a suitable material, and we will see very soon how. Now, it is wavelength dependent. It is not going to measure heat. It is going to measure that particular wavelength which we are interested in measuring. Now, here cooling improves the spectral sensitivity of the material. Now, and also these sensors can be made to be at very high frequency of operation. You can also go up to gigahertz of frequency. So, if you remember, this is the effect which gave Albert Einstein his Nobel Prize, right? Though we remember him for his theories of relativity, the special and general theory, it was the photoelectric effect which got him the Nobel Prize. So, if you remember from your high school days, and photon with sufficient energy hits a substance, it passes the energy onto it. If my energy is high enough that the electron could move, then I get a photoelectric current. Another theoretical foundation there, you had remember concepts of band gap. Has it been taught to second year students? Right. So, you recall things saying that insulators, so there are bands of energy where we know electrons are there. There are bands of energy, if they have this energy, they will start moving. So, the valence band which I am there, conduction band is when they will move. So, for insulators that band is quite big. So, you need to give a lot of energy for electrons to move and to conduct electricity. For semiconductors, this band is moderate. For metals, these bands overlap. So, electron is always available to carry conduct. Now, the moment you apply a potential difference, the electron is happy to move. For semiconductors, it is in between. Now, this band gap comes into play very interesting. So, the photon should have enough energy to overcome this band gap. So, now band gap of silicon is 1 point, well, what is the band gap of silicon? Sorry. Let us do the reverse calculation. Here I have done the forward calculation. So, if we take the band gap of silicon, let us try to calculate what is the highest photon it will be able to measure. Okay. So, what's the band gap of silicon? If you don't know, do a Google search. It's perfectly fine to find resources from it, and all of you guys are carrying mobile phones anyway. So, can somebody give me the band gap of silicon? You have your mobile phones? 1.12 electron volt, right? So, that is the energy I have. So, that is the band gap I need to overcome. Now, the question is, what is the highest wavelength I can measure with 1.12 electron volt, right? So, you have 1.12 electron volt on one side and you have Hc by lambda on the other side. Let us try to find what will be the lambda. So, Hc by 1.12 electron volt, and somebody can do that calculation. You have your phone, so you can even ask Google to do that calculation. That is perfectly fine for me. Now, will Google do it? If you just enter Hc by 1.1 electron lambda, does it do that? How much is that? Throw a number, worst case it will be wrong. You can see all the eyes are looking down. The moment you look up, you see eye to me, so you have to give an answer. Actually, you know what? While you are doing that, I will also do it, and let's see how hard can it be. (1100 watt units) nanometer. So, 1.1 micrometer. Actually, while you guys were doing this calculation, I found a web page which does photon energy calculation. Did you find that as well? And you just enter the energy and it gives you the photon. Were you able to find that? Okay. Good. So, that was till 1.1 microns my silicon could do. But actually, in the early stages, its sensitivity is not very high. The sensitivity goes from 0 onwards. For some reason, some of the reasons are these. Not every photon gives birth to electron hole pair, because we have something called photon detection probability. Some photons will just pass through. Right? It's not that immediately the first photon material it hits, it gives birth to the electron hole pair. There's something called penetration depth. That is the depth on the structure. So, photons are coming with an energy, right? So, they try to penetrate the material. So, at some penetration depth, do they pass on their energy to them? So, because infrared photons have got decent energy, they try to go deeper. So, their penetration depth is higher than, say, ultraviolet photons. So, if you make a structure which is very, very thin, even though its band gap will be fine, the photons will pass through, or a large number of photons will pass through. Now, let us ask the other way question. Now, somebody of you will have the Omni calculator on your phone anyway, right, which finds this thing. So, our near infrared goes from about 780 to 3 micrometers. Okay? We said silicon will work till 1.1 micrometer. After that, it doesn't work. If we want to find 3 micrometer, what material should we use? Okay, it's the inverse question now. In order to do that, the first thing we need to do is to find the photon energy there. So 3 micrometer, what's my photon energy? 0.4 electron volt, and you can do the same calculation again. So I'm not going to bother you with calculations. Okay. Now let's try to find a material. So let's do a Google search again, because rather than throwing a material chart, so let's look at or just do a search for band gap of typical materials, typical semiconductor materials, and see if you find a semiconductor material whose band gap is small. Now we need a small band gap material for these things. Okay. So you should be able to find a table somewhere which lists band gap of typical materials or typical semiconductors. Did you find something? Lead sulfide. Okay. What's the band gap of something like indium nitride? Or indium arsenide? How much is indium arsenide? Tell me the number. 0.36 electron volt. Now the other thing which some of you might have known that in so silicon is a group 4 material, if you remember your periodic table, right? So what else do we have in group 4 other than silicon? We have carbon, we have germanium. So germanium exists as a semiconductor, carbon exists as a semiconductor in a very fancy fashion. It's a very interesting material. It can be a conductor, semiconductor and insulator all at the same time depending upon how you build it. Little wonder we all are made of carbon, right? The other way to make semiconductors is to take one material from group 3, another material from group 5. You also have two 6 semiconductors, one from 2, one from 6. Now most of the tables which you would have seen would be typical materials. Now people also do something called band gap engineering by introducing sufficient dopants to try to change the band gap of the material. So suppose you try to merge aluminum in it. Okay? But these indium based sensors can act on these devices. Can we go even higher? Can we go till mid-infrared? So you have got a table on your phone, mid-infrared goes till about 0.21 electron volt. Can we use such materials for that kind of sensors? Is there any material which can do that? Now that would be lead based, which is found anything which can go to that level? I will also do search for you. Now, generally I can give you these in a table. And what I have found, the moment I put a table, people's brain go to sleep. That's why I make you search, do something. Have you guys covered direct band gap and indirect band gap in your semiconductor physics till now, or not yet? Okay, if not yet, we'll stick to standard materials. Lead-based materials can act as a large infrared sensors. So now you can see the problem here. The more is the wavelength, is difficult to find simple materials. Why the band gap is there, we can discuss this in a later lesson. But for the time being, at least in near infrared, we have got a lot of material which we can use. In your table, you would have seen a large number of material which have got this band gap in this 1.59 to 0.4 electron volt regions. And people often divide this near infrared also in different bands. It's not just one big band. So you'll have sensors around 1 micrometer, 2 micrometer, and so on and so forth. Okay? So let's start looking at the type of devices which are made here and what are the things which is required. Now, yesterday we talked about resolution. Now, for these sensors, there are two things which are of interest to us. One is the temperature resolution. If my temperature is changing by X, what's my signal changing? That's fair enough. The other is spatial resolution. Remember, when we take cameras, we put large number of pixels and we call it resolution because this then determines what's the smallest distance in space I am taking a picture of. Right? More pixels, the area, I'm taking the same picture with more pixels, which means each space is denoted by higher spatial resolution. Now, historically, IR cameras have lagged significantly behind visible cameras on their spatial resolution. Say you can get a 100 megapixel visible camera, but 100 megapixel IR camera is very difficult. Even few megapixel IR cameras are difficult to get. Unless, of course, you are a military contractor and you are making just one IR camera for one particular thing and you can charge a couple of million euros for it. Okay? So, spatially speaking, IR cameras are still lagging behind their visible counterparts. By the way, can somebody figure out what's cadmium-based materials band gap? Cadmium, indium telluride for that matter? That's another nice material to use for IR sensors. But anyway, okay. Now, the way we design IR sensors is so in case of visible sensors, we have kind of standardized our design now. It's silicon-based, few transistor pixel circuit, and we have made a fairly standard approach of designing them. In infrared, that has not been the case. It has also not been the case because there are different ways of measuring infrared. And there are a large number of physics-based things which happen here. So there is Seebeck effect, which essentially says if we have some materials which are at two different temperature and you connect a wire between them, you will see electrons will flow as an effect of the difference in temperature. Okay. There is pyroelectric effect, which says that if my temperature changes, that leads to a voltage in some materials, not all the materials for that matter. And there are parametric sensors which somehow manage to change voltage or current based on temperature based effects. These could be changing resistance based on temperature. Now, we know most resistances are temperature dependent. Such sensors are called bolometers. They could be changing pressure. Such sensors are Golay cells. They could stretch a material, and there are many such. And even something as simple as the forward bias voltage of diode. Remember, you have done quite a lot of diode equations and transistor equations. Temperature always appears one way or other. If nothing else, Kt, where K is the Boltzmann constant and T is the temperature, appears at many locations. So wherever it appears, you know whatever my output of semiconductor material is going to be, it's going to be temperature dependent. So I can use that as a temperature sensor. So if nothing else, you take a diode, just design a simple diode, measure its current, that is a temperature sensor, if we can dissolve it into very small amounts. Does anyone remember the diode equation? How is it related to temperature? So the forward bias current is Is e to the power KT something. That's what I said 5 minutes ago. You guys should be better than me, right? I did these courses 25 years ago. It's the I naught term which appears there. That is the heavily temperature dependent. Okay, so I naught times e to the power voltage something. There's that. Actually, we will see it's not a very easy relationship with temperature. As a rough rule of thumb, we say for every 10 degrees Celsius it doubles. So it's an exponential kind of change, but that's a rough rule of thumb. It also depends upon what type of diode you have, what material you have made. So some of you might have seen things like this in mechanical engineering lectures, wherein we may use the Seebeck effect. Essentially, we use two different material and put one material in hot, one material in a cold place, and the other material is looking at your heat, and then most material will have some Seebeck coefficient. Here you have got alpha A. There was a pointer here which has disappeared. I can't move my mouse here. So alpha A minus alpha B, whatever is the temperature difference between these two materials will lead to a voltage being induced in the output line. Okay. Now generally the voltage produced by just one thermopile is quite small. So whenever you have one sensor producing a small response, there are 2 or 3 things which you can do. You can either put an amplifier after that, or you can try to increase the amount of response by putting sensors in series. So one is producing a small amount of volt. If I have n number of these, then I will get n times that voltage. Okay. So quite often we make series of these, particularly when we are making in chips. Now these sensors have been used for last 50 years, or if not 100 years. They are nothing new. But what we are going to discuss is how do we put it on top of a silicon chip. So to do that, I mean, here are some examples of doing that. This is a microelectromechanical sensor chip, wherein you can see they have got a hot junction and a cold junction, and they are trying to keep these structures away from one another. And if you look at the literature, there are tons of such papers. Okay. Here's another example of this, wherein you have encapsulated your cold structure in a structure, and then you have made a 3D structure on top of that. I gave you these examples just to show in the microelectromechanical system world, people where they are trying to make smaller mechanical structures, and they have freedom of the kind of structure they do. There has been a large number of such sensors which have been built. But before that, let's try to figure out, so here we need 2 different type of material, right? One which has, and ideally it would be good because the voltage produced is the difference of their Seebeck coefficient times temperature. So ideally what we should make is these 2 materials having large differences of their Seebeck potential. Then I will get high voltage. And my apologies, now I am going to bore you with a table. So here are some materials which we have available in the CMOS process itself. I am making out of silicon. I have got polysilicon. I have got silicon on insulator, SOI. And then I can dope them with N-type or P-type. Okay. So doping then changes my Seebeck coefficient. So from here, I mean, you can see things like silicon on insulator has got fairly high Seebeck coefficient, but it's a bit negative. Polysilicon seems to be fairly good there, right? It's 190. units volt per microvolt per Kelvin. And it's available. We made using polysilicon, we made the transistor. So I don't need to introduce a new material in my process. So other things like bismuth telluride, which are on top, they're not inherently available in a silicon process. Right? Even silicon on insulator means I have got an insulator base, then a dielectric, and then silicon. It's a costly process to make. So people used to make chips on things like silicon on sapphire or silicon on diamond. But polysilicon itself is available. So I already have one material. Now I need a second material. So one I selected 190. The other would be good, either it has got 1000 or 1. Right? Then I have got a good range, isn't it? So here is the characteristic of some other materials here, and you can very well immediately see that metals, or at least some of the metals like aluminium or gold, have got very low Seebeck coefficient. So if I already choose polysilicon with around 190, or if I can dope it nicely, I can also get slightly higher. The beauty of some of these metal is aluminium or gold is tricky to introduce in a CMOS foundry, because gold ions start diffusing in silicon and start changing the transistor properties. But yesterday when we were doing, at least those who were doing layout, they saw we had metals, metal 1, metal 2, metal 3. In most larger processes, we used to use aluminium as a metal to connect transistors. This is very interesting because I already have polysilicon and I have aluminium, which means I can make such sensors on a classic silicon chip without introducing any other material. The whole crux of my course is, what can we do on a silicon chip? You can have fancy materials and we can add loads of these things. But if we take one beam of aluminium, other of polysilicon, we have got a thermopile kind sensor design. And there are a number of such commercial sensors in the market. So you can go and have a look at these and you will find some things, a lot of these are there in the market there. The problem of these is twofold. One, you need to cool a junction or keep a junction cool. Right? So you need to shield it somehow from incoming heat. Classic sensors, in diode sensors, all the diodes were open. They were just receiving light. If my cold junction also gets hot, that will be not nice. So quite often, such sensors are made with one sensor on a chip. You are essentially looking at just the amount of heat. You are not looking at a particular radiation. You are not trying to take a heat map. You are trying to measure heat overall in the room. The other thing which is often designed is pyroelectric based sensors, and then you have got another property to look at for pyroelectricity. Okay. Here if you look at things like aluminium nitride, do we have aluminium nitride here? We don't, but you have got pyroelectric coefficients, if you look at the last column, of quite a lot of ceramics. Now, where do we use ceramics in silicon processes? So, till now we did not talk about how you package a chip. A chip comes packaged, and this is where we will be using quite a lot of other things. Now, people have tried making pyroelectric sensors from aluminium nitride, because again aluminium was available in silicon process, but it has not been a fairly good success because aluminium nitride itself has a very low pyroelectric effect. Doping it, something with scandium, making it a scandium aluminium nitride, that has been a fairly decent success, and people have tried making structures like this for, you have got a titanium, different electrodes, you have a sensing layer in between. So, trying to make a pyroelectric sensors on those kinds. The sensor which I believe has the most prominent use will be bolometers, and that is the one which I will be covering in a bit detail. So, the word bolometer comes from bole, which is Greek for beam of light. And these sensors work in a much simpler fashion. Essentially, their temperature, their resistance changes with temperature. Okay? And we have a temperature change coefficient which is 1 over RB delta RB times delta Ts. So, how much does my temperature change at a given, how much does my resistance change at a given resistance as my temperature changes? Now, this temperature coefficient of resistance for metals is positive, which means more temperature change, more does my resistance change. For semiconductors, I have written it negative. It's not purely negative, but in most room temperature, it is kind of negative. Why would you think the resistance of a semiconductor will reduce as I increase my temperature? Sorry? So, why is that not happening in metal? Metals also you have electrons which can move freely, right? So, one argument, yes, is high the temperature, more energy electrons have, they can move faster. But then metal resistance should also fall down. But we know standard resistors, their resistance increases with temperature. So, the bottom line there is the more temperature you have, the more thermally generated electron hole pairs are being generated. In semiconductors, you have got larger number of charge carriers available to carry current. If more charge carriers come in, your native resistance falls down. Good. Now, look at the temperature coefficient of resistance for various metals and various semiconductors we have. Metals like aluminum and copper we have in the process, and they have very similar temperature coefficient of resistance. So, percentage change in temperature is fairly smallish. For semiconductors, we have got bigger changes here. Okay? And some semiconductors, something like gallium arsenide, they have got very good number compared to metal. Okay? Now, gallium arsenide is used for making a large number, not larger, but decent number of electronics, particularly high speed electronics. We use 3-5 semiconductors, though their use is reducing with time, but they are still there. Now, for some maths. We have done this lecture till now without maths, so some of you might be feeling a bit bored, right? So, we are now going to look at heat conduction equation. We have one mechanical engineering in house. You can explain this better than I can, right? You guys should have done thermo heat flow. And he's saying, nah, don't remind me of the bad days of looking at laws of thermodynamics, the 3 laws which still taught, isn't it? You guys were taught laws of thermodynamics. Sorry? So, you have forgotten it by the time you start MTech. The classic heat conduction equation is the one equation on top. There are few things to look at here. C is the heat capacity. Essentially, it is saying how much radiation is being converted to heat. Not all of that will be converted into heat. Okay? Next is thermal conductance. That is basically saying, so I have got a sensor and I have got my environment. What is the resistance between environment and me? It could be environment or it could be a heat sink, somewhere where heat is going. And last is, of course, the absorbed radiation power, and that is with an exponential attached to it. Now, this is a simple differential equation. It's the first order differential equation, right? So, all of you should be able to solve this. I am not going to bore you with solving this. You will get a relationship something like this. A delta T would become a function of incidence radiation, the conductance, and a time constant here. The time constant would be a fraction of your heat capacity and thermal conductance. Remember we did lumped mass models where we looked at thermal effects as well. So, I will be talking in terms of electrical properties here. As temperature of the so temperature of the sensor will rise with a rate of P incident by C. So, you see we have from this relationship you can come up with that. The limiting value would be a steady state value where actually plus some whatever is the incident radiation divided by my heat conductance. So, I will reach a steady state value in due course of time and you might have seen as we start heating we will reach at one point of time. Typically, if you have long cylindrical devices like wires, that is the kind of heat conductivity equation you have, which looks very similar to the resistive conductivity. So, what is the resistance of a cylindrical wire? Rho A by L. Sorry? So, area of rho L by A, right? So, L being the length of the conductor, area being the area of cross section. If you look at the conductivity, it will be 1 over R A by L. Electrical conductivity. So, the thermal conductivity has a similar formulation as the electrical conductivity. And of course, we define a constant here which then tells us how it proceeds. Now, from there we could calculate the responsivity of the sensor because we wanted to find what's that what's the temperature coefficient of resistance, and that comes out to be a fairly simple number where you have got G which is in the denominator. Now, there is something else which one should remember when we have got a sensor whose temperature, whose resistance is changing with temperature. Now, generally we measure electrical sensors by passing a current through them. So, if my resistance is increasing, what is increasing? My voltage demand. Okay? Agreed? So, we said metal based sensors, their resistance increases with temperature, which in turn means my voltage demand is increasing. Now, if it increases to a very high value, I will need a very high voltage or I will be having very high amount of power dissipation. So, this leads to a pole in the equation. Now, I am not going to do the equation for you, but think of it this way. If I pass the same current through the sensor, I have fixed my current, my resistance is constantly increasing, which means I am dissipating more and more power. So, at some point there is a risk I might burn out my device, I will be dissipating more heat. Now, semiconductor sensors, that is where they come nice, because their resistance is decreasing with temperature. So, I do not have to worry about this burnout effect or there will be too much heat which will be moving this thing. So, that is the relationship. So, 2 is the waveform which shows what happens to the voltage, what happens to metal based sensors, and then this is voltage by current. So, we are plotting the resistance here, okay, versus what happens to your semiconductor based sensors. So, you can see the power dissipation or the burnout effect in semiconductor based bolometers would be better than pure metal based bolometers. And that has been the trend as well. We are seeing more and more. Now, this is a very good trend. It plotted things like how are resistance based sensors working compared to diode based sensors. That is one. So, as said right in the beginning, you can use a simple diodes current also as a temperature sensor. So, if you just look at various sensors which have been proposed versus their pixel size. Now, why would we want to reduce the pixel size of sensors? Smaller is the size of the sensor, large number of sensors I can put on a chip. Now, bolometers are interesting because essentially you can do an array of bolometers. So, you can take an image. Little wonder diode based sensors, their size is reducing because we can make transistor processes in smaller and smaller geometry. But the other thing worth checking is, what was the size of the diode sensor which we took in while designing camera pixel? 3 micrometer by 3 micrometer. These are still significantly bigger than our camera pixel. We are looking at 20 micron, 60 micron, or that kind of sizes. So while we can make an array, the individual pixel is still comparatively larger, which means the number of pixels which we will have is still fairly small. Now earlier, this is how we were making our bolometers. Typically you will have a metal absorber, my brain is dead today. And then you could design, if you're designing of amorphous silicon is, remember we looked at the temperature coefficient of resistance, silicon was fairly good, and we designed something like a 100 nanometer thick structure which is sandwiched between two dielectrics. So if you look in this structure, you have metal absorber on top, silicon dioxide are dielectrics, and in between we have amorphous silicon, which is a semiconductor, which is acting as a sensor. Or people were using some sort of vanadium oxide together with silicon nitride. Okay? And this is how you will be typically be making an IR absorber. So if you are making, say, here is an aluminum based thermistor, you will create long arrays of it, because you want as big an area as possible. The more the area it has, the more heat it will absorb. And making these fingered structures help you increase the area of the structure. And this also gives you longer length while keeping area of cross section small. A typical diode based bolometer would be something like this. You can see there is a PN junction there, and then you have an absorber layer, a heat absorber layer, which is to typically be made of metal. A number of these are not made in classic silicon processes. We use silicon on insulator processes. We want a good thermal material below which is not getting itself heated. We would want the sensor to be heated, not the package and not the substrate on which it is. Good. Then is the question of, so that was a sensor material which is less of an interest to us. We know we have material. How do we read it out of this? So we know a voltage is changing or current is changing, because the temperature is changing the resistance, which in turn will change my voltage or current. If I apply a fixed voltage, current will change. If I apply a fixed current, my voltage will change. So what kind of circuitry we have applied? So direct injection circuits are very similar to pixel circuits. So we designed a pixel circuit in the lab yesterday, right? We had a diode, few transistors. For bolometers, you can kind of design the same circuit. Right? You take the current produced by bolometer, integrate it on an external capacitor. Now, in case of image sensors, we are using diode as something which was measuring the current. Diode itself has a capacitance. So we are integrating that current on the diode capacitance. If we are using a bolometer based on another material, not a diode based ones, then you have to build an external capacitor to integrate that charge on it. Such devices can be made. They have been seen to have poor linearity and they are a bit noisy. A better solution could be not to measure. They are a bit noisy because now the capacitance which you have is coming in parallel with my bolometer. So whatever I am integrating is also affecting the bolometer operation. So one operation could be to buffer my sensor from rest of my electronics. And because it's a current based sensor, we can put a current mirror which hides the rest of the electronics with my sensor. I was going to cover the last topic, which is capacitive transimpedance amplifier. They work even better with bolometers. Basically, you are converting a capacitance into a voltage output. So this is an op-amp based circuit which you can build. Now you can immediately see why, some of the reasons why our pixel is not becoming smaller. All these circuits consume a large number of transistors. So if you're making a transimpedance amplifier, that will be about 20 or 25 transistors. So you have 25 transistors, an array of 25 transistors, which inherent area will be bigger. So despite the fact bolometers can be made very nice and can be made smaller compared to others, the individual size is still struggling. We had a project in Glasgow where we tried to make a visible camera and infrared camera below that. So the idea being infrared has got energy which will pass through visible completely. So we make a camera below that so that it passes through the visible part. And we thought we can take the image and we can take the visible image as well as the infrared image at the same time. Two problems happened. One was we could make the visible pixel very, very small. So I'm taking the scene with say 1 megapixel, but I only have 10,000 infrared pixel. So how do I correlate the infrared part with the visible part? I mean, think of it this way. You take my picture, okay? A normal camera will tell you, the picture taken will be easy to identify where my nose is, where my ears are, where my eyes are, because I have got tiny pixels, or the retina in my, not the retina, but you can see the eyebrows and the other things. But if your infrared pixel has got less resolution, maybe my whole eye is coming out to be 1 pixel. So finding boundaries becomes very tricky. How do we correlate these two? The other thing is the optical assembly. How do you make lenses for these, something which covers the whole broad spectrum? So as a sensor wise it works, but broadly speaking as a system wise we had difficulty. So right now most people will try to put two different sensors and try to take an image if you want to merge infrared and visible image together. It has been an active area of research because if you just look at a human being, I have an infrared profile and I have a visible profile. Right? So these two could give me some more information. If you go further high, if you look at terahertz sensors, then you can look at things which are just hidden below my skin or below my cloth. Some of these sensors are already there in the market. So if you go to some of the airports, you have these sensors which take a picture of you and then try to identify if you have got concealed things in your trouser, if you have concealed metal in your trouser, if you're carrying a gun or something. Okay? They haven't reached very deep internal objects. People are also looking at sensors which can look just below your skin to look at things like skin pigmentation to identify early signs of skin cancer. All of this comes from these sensors whose penetration depth is different. Right, we have been talking for an hour. By now I'm sure you are tired. So we'll take a 10-minute breather and then we'll come back. Okay? Sir? Can we stop the video recording? For the time being.